concept called principal stresses and maximum in-plane shear stress. First, we look at principal stress. So, what does principal in-plane normal stress mean? The maximum and minimum normal stress in a plane at a particular point is called principal in-plane normal stress. One thing which we have to keep in mind that when we talk about principal in-plane normal stress, the value of shear stress acting in the same plane is taken as 0. So we only talk about normal stresses which can be maximum or minimum in a given plane at a particular point. Now to derive that, let us move on to the whiteboard. In our high school, we would have come across something called critical points in our calculus classes. We would have come across something called minimum and maximum points, in which if I draw a quadrant and if I have d of f by d of x equal to 0, then if we have a graph like this, the truss and lowest point are given as 0, which is the maximum and minimum point. Here we can say that this is the maximum and minimum point. So now from the previous derivations, we know that sigma x dash is equal to sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 into cos 2 theta plus tau xy sin 2 theta. Now to get our maximum and minimum values, we'll differentiate both left hand side and the right hand side with d theta. So therefore d sigma x dash divided by d theta is equal to d by d theta of sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into cos 2 theta plus tau xy sin 2 theta. So we know that the value here is 0. So 0 minus 2 into sigma x minus sigma y by 2 into sin 2 theta plus 2 tau xy cos 2 theta. Now this is our value after differentiating. Because we have equated this equation to 0, we can take in left hand side and right hand side consideration and we'll get 2 tau xy cos 2 theta equals 2 into sigma x minus sigma y by 2 into sin 2 theta. Now here, if we again reorder the equation, we'll get tan 2 theta. We get tan 2 theta here because if cos and sin are reordered, and we know that by trigonometry tan is equal to sin by cos. So therefore tan 2 theta is equal to tau xy by sigma x minus sigma y divided by 2. Now because we are working with normal stresses wherein we have to consider both tau and sigma, and in this formula we can see that we have both the variables tau and sigma. When we plot this tan 2 theta value in a graph of tau and sigma, we'll get something like this. So if I take a graph of 4 quadrants or coordinate of 4 quadrants, wherein the vertical axis is tau and horizontal axis is sigma, the plot is going to be a triangle wherein the horizontal value is going to be sigma x minus sigma y by 2 and the vertical value is going to be tau xy. And when we plot it for 2 theta, we know that tan is equal to opposite by adjacent. And at the same time, from the Pythagoras theorem, the hypotenuse can be written as root of sigma x minus sigma y by 2 the whole square plus tau xy the whole square. Now going back to our stress equation where sigma x dash is equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into cos 2 theta plus tau xy sin 2 theta. Now going back to this formula of ours, now that we know what values we have in the hypotenuse, opposite and adjacent side of 2 theta, we can substitute values for cos 2 theta and sin 2 theta because we know that cos theta is equal to adjacent by hypotenuse and sin theta is equal to opposite by hypotenuse. Now after substituting and simplifying, we get sigma x is equal to sigma x plus sigma y by 2 plus root of sigma x minus sigma y by 2 the whole square plus tau xy square. Now because we have values in both the quadrants and we know that the in-plane normal stress is both maximum and minimum, we have one more triangle to take care of with the same 2 theta. And now here our tau value is going to be minus tau xy and same way our sigma value is going to be minus sigma x minus sigma y divided by 2. Because we have two values to consider but only change that is happening here is in the direction, or you can also call it as negative and positive signs. So the only difference that comes here is in the sign convention. We can generalize the formula as sigma 1 comma 2 is equal to sigma x plus sigma y divided by 2 plus or minus root sigma x minus sigma y by 2 the whole square plus tau square x y. We can see here that after we substitute the values of cos theta and sin theta in the sigma x value, and we know that there will be two values given because of sign convention, we'll get this equation which we finally arrived upon. So some of the observations which we have to take care is that sigma p1 and sigma p2 are 90 degrees apart from each other. And there are no shear stresses at the point of principal stresses. We already saw that principal stress is only the maximum and minimum point of normal stress that is happening in the principal plane. Also, we should take care and we must test the value of theta p to ensure that the value of theta p1. Now we'll move on to maximum in-plane shear stress. So as for maximum in-plane shear stress, it is exactly similar to what we saw with in-plane normal stress, but this time we are going to use the third and fourth quadrants. So in the first normal shear stress, we were using the first and the third quadrant. This time we'll be using the second and fourth quadrant. And by doing the same calculations, just that we will change our parent equation for the shear stress equation, which is tau x dash y dash. We'll arrive at a tau maximum where it's maximum in plane, and that will be root over sigma x minus sigma y by 2 the whole square plus tau xy the whole square. And here we should also note that we'll get an average value which is sigma average, that will be equal to sigma x plus sigma y by 2. We get average value when we don't have shear stress with us. And the observations which we have to note here is that theta P and theta S are 45 degrees apart from each other. And at the point of maximum in-plane shear stress, there is a average in-plane normal stress. So next, we'll go ahead and solve a problem. The statement given here is for each state of stress given, we'll have to determine principal stresses and their orientation. And we should also figure out the maximum value of in-plane shear stress and average normal stress and their orientation. Now, this is going to be a straightforward problem. Let us again jump into the whiteboard. So, from the question statement, we need to figure out principal stresses and their orientation, and then we'll have to find the maximum value of in-plane shear stress and average normal stress and their orientation. First, let us note down the given values. So, from the diagram, sigma x is given as 2 ksi, and then sigma y is given as 10 ksi, and tau xy is equal to minus 3 ksi. So first let us write the equation for principal stress, which is sigma p, that is equal to sigma x plus sigma y divided by 2 plus root of sigma x minus sigma y the whole square plus tau xy the whole square. With that, if we substitute the given values, which is 2 plus 10 by 2 plus 2 minus 10 by 2 the whole square plus minus 3 the whole square. So we'll get the value of sigma p as 11 ksi. Now when we do the same thing, so this is for sigma p1, we know that this formula is plus or minus formula. So we first did it for sigma p1, and let us consider the positive sign convention here. In the same way, for sigma p2, giving a negative sign convention, we'll get the value 1 ksi. We got both p1 and p2. Our next step is to determine the angle of orientation. Now, for that, we know the formula T tan 2 theta p, which is equal to tau xy divided by sigma x minus sigma y by 2. By substituting the given values here, we get 2 theta p as 36.9. So we came over few observations which was given for principal stress or for plane normal stress. The 2 theta value ranges inside plus or minus 180. So basically 2 theta p1 to 2 theta p2 falls under plus or minus 180. So therefore, if we get 2 theta p equal to 36.9, then we got one value of 2 theta p as 36.9. Then if it falls inside 180, then it should be 2 theta p, which is equal to minus 143.1. So what we have done is, we have subtracted the first value from 180. Again, from the same observations, we also got that theta 1 to theta 2 values fall under 90 degree. Again, if 2 theta p is equal to 36.9, then theta p is equal to 18.45. Therefore, one more theta p value should be 90 minus 18.45, and it is minus 71.55. Now here, if you can see, I have given one positive value for 2 theta p and one negative value for 2 theta p. In the same way, I have given one positive value for theta p and one negative value for another theta p. This is because we know that the normal stress should be falling as one negative and one positive value, because we have a quadrant in which this is positive and this is negative. Now with that, to figure out sigma P1 and P2, we'll again substitute the theta value in the normal stress equation that we saw earlier. So the stress equation which we saw earlier was sigma x dash is equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sine 2 theta. So this is tau. So after substituting whatever values we got, and let us take 18.45 as our first value to substitute here, and we'll get sigma x dash as 1 ksi. Now sigma x dash is equal to sigma p2, right? So sigma x dash is equal to sigma p2. Therefore 18.45 is theta p2, and the value of theta p1 will be equal to minus 71.55. Now as for the orientation, so if we take a straight line, then the angle between this is, for example, minus 71.55, then the oriented plane for minus 71.55 degree angle is going to be this, wherein sigma p1 is equal to 11 ksi and sigma p2 is equal to 1 ksi. Now both of these sigma values are positive values, and that means that the stress is also outwards. And if these are negative values, we are going to draw stresses which are inwards. So our next statement is to find out the maximum value of in-plane stress and average normal stress and their orientation. So we'll take the next slide or the next board. As for the in-plane shear stress, the formula for in-plane shear stress is given as tau in plane is equal to plus or minus root over sigma x minus sigma y by 2 the whole square plus tau xy the whole square. We already know the given values, and if we substitute all these values inside, we get a value of plus or minus 5. Our next plan of action would be to find out the theta value, and that can be found out using tan 2 theta formula for shear stress, and that will be tan 2 theta is equal to minus sigma x minus sigma y by 2 divided by tau xy. After substituting, we'll get tan 2 theta as 4 by minus 3. Now 2 theta will be equal to minus 53.13 and theta will be equal to minus 26.6. Now we got one of the theta values. We also got the value for in-plane shear stress. Next, we'll figure out the average stress, which is sigma average. That will be equal to sigma x plus sigma y divided by 2. And after substituting, we'll get 6 ksi. So now to figure out the shear stress, if it's positive or negative, we'll substitute the theta value in the original formula. The original formula for tau x bar y bar is equal to, or tau x dash y dash is equal to minus sigma x minus sigma y divided by 2 sine 2 theta plus tau xy cos 2 theta. Tau x dash y dash is equal to minus of 2 minus 10 divided by 2 into minus sine 53.13 plus minus 3 into minus cos 53.13, that will be equal to minus 3.19 plus 1.8, which is equal to minus 1.39 KSI. As for the orientation diagram, we can say that our normal stress is a positive value which we got from the sigma average calculation, and because it's a positive value, the arrows can be drawn outwards, and that is going to be 6 KSI. Our shear stress is a negative value, due to which our shear diagram or shear arrows can be drawn clockwise, which can be given as minus 1.39.